We just completed our 3 sections dealing with rational expressions and how to use addition, subtraction, multiplication, and division in an effort to simplify them and determine the domain restrictions. Now we're getting into rational functions. A rational function is a function whose root can be written as a ratio of 2 polynomials. At the parent function, if you recall back from section 1.9, we at the beginning of the year, the parent function is 1 over x. And when we start getting into rational functions, we get something called a hyperbola. And a hyperbola is simply the graph of a rational function. It has a curve that consists of 2 distinct and similar branches. And you don't need to know that per se, but know that it's called a hyperbola. It's called a hyperbola because it's a hyper variation of a parabola. Now, we're going to start looking at asymptotes today. It's a line on a graph that a graph approaches but never actually touches, and they can be vertical or horizontal. And then finally, the last piece is known as a hole. And a hole is when there's a binomial in both the numerator and the denominator, such as x minus b, and therefore x equals b as a whole, unless it's a vertical asymptote, and we'll get into all those details later. So let's take a look first at how we determine the domain and the vertical asymptotes of a function. So we have here f of x equals 2x plus 1 over x minus 9. We need to get the domain and the vertical asymptotes. Our step 1, our domain is going to be all x values except where the vertical asymptotes exist. And it's written in the form of bracket x bar, which means x, all x such that x cannot equal whatever your vertical asymptote is. Now, the actual fact of the matter is we need to do our vertical asymptotes first, which you've actually been doing. These are, and you can make a note of it, these are actually your domain restrictions. And so where the denominator equals 0. So in our case here, we have x minus 9. And so therefore, x minus 9 cannot equal 0. Therefore, if we solve this, x cannot equal 9. That means we have a vertical asymptote at x equals 9. And when we write our domain, we're going to have a bracket of all x values such that x cannot equal 9. And I know these look like they contradict each other, but that's because the vertical asymptotes tell you where x values do not exist, and the domain just affirms that by saying x cannot equal that. Moving on to the next example. In example B, we have 2x cubed minus 5 over x squared. Remember, we cannot cancel this x squared with this x cubed because this subtraction sign is involved. So therefore, because that is the case, we need to go ahead and say, all right, x squared cannot equal 0. Therefore, x cannot equal 0 because the square root of 0 is 0. Therefore, we have a vertical asymptote at x equals 0, and our domain is all x such that x cannot equal 0. So remember, your domain and your vertical asymptotes have to match. Looking at our last example for today, I see that we have, in this case, we have that x plus 1 cannot equal 0, and x minus 5 cannot equal 0. Therefore, x cannot equal negative 1 or 5. So we have vertical asymptotes at x equals 5 and at x equals negative 1. Now when we look at the domain, I like to write the vertical asymptotes separate, but I can write the domain together, where we can say all x values such that x cannot equal 5 or negative 1. In the next video, we'll take a look at range, horizontal asymptotes, and holes.